Hi, I'm Antonio Sala, and in this video we are going to continue with the study on how to obtain the largest ellipse into a given convex shape with lines and ellipse segments as boundaries. In particular, this is the shape. We are going to consider the interior of the black boundary, and we are going to consider just the case which is symmetric around the origin. So the straight lines conforming the boundary are given by this kind of linear inequalities, and we can just square them one by one, row by row, and obtain these quadratic inequalities. And of course, if we replace this thing, which will be rank 1 in the line edges, if we replace that by any non-singular matrix, then we will have the shape of a non-degenerate ellipsoid, such as this one. So this intersection of ellipse and polygon can be considered an intersection of ellipses, some of them degenerate. So good. In a first video, we thought in describing my candidate ellipse by this expression and P being a decision variable, a symmetric 2 times 2 matrix, so that we need to find P fulfilling these inequalities for it to be inside each of the ellipses or degenerate ones in my boundary, and then we optimized something related to P, either minimizing the largest eigenvalue, which is equivalent to inflating the minimum radius, or we can minimize the trace of P, which is equivalent to inflating the ellipse by somehow sum of the inverse of the semi-axis lengths, which is kind of strange. But well, these were the kind of solutions we obtained with my target ellipse represented in this non-inverted form. However, in order to maximize the area, it can be proved that the area is inversely proportional to the determinant of P. More on that in a minute. So maximize the area of P would be equivalent to minimizing the determinant of P, but that is not a convex optimization problem, and hence we will make some manipulations to render the problem convex, and the manipulations will be as follows. If we recall, we have these bands, each of the rows of AI in these inequalities that we squared to these quadratic ones. So, if my candidate ellipsoid, ellipse in this case, was this thing, then it was inside the band if, and only if, the matrix P was larger than this thing, so the ellipsoid was smaller than the band. So my largest area would be equivalent to obtaining the smallest P, the P with smallest determinant, while being larger than these things. But determinant minimization is not a convex problem, but determinant maximization is a convex problem. So instead of minimizing the determinant of P, we can maximize the determinant of P minus 1. So we will search for an ellipse in the form like this, and my decision variable will be Q, the inverse of P. But then we need to change my LMIs because, well, the inverse operation is not a linear operation, so we cannot use this kind of conditions in my linear matrix inequality solver. So how can we do it? Well, if this were a non-degenerate ellipsoid, well, I will express everything in inverted form. I will call the thing in the middle m-1. Then if m-1 existed, which is not the fact here, we are not lucky, but if m-1 existed, then the larger m is, the larger the ellipsoid is. And then in this case, in inverted form, the inclusion of ellipses can be encoded as the inequality in here. Matrix Q must be smaller than M because the size is proportional to square root of Q or square root of M. But in this case, then this would translate to Q less than the inverse of this thing. Okay, if this was M minus 1, then M is the inverse of the thing. And we have a problem because that stuff does not exist. So we cannot encode the thing in pink because this thing would be infinite, and we cannot put infinite into my numerical optimization routines. And we cannot encode the red highlighted thing because it's not an LMI. So are we in a dead end? Well, something called Schur complement will come to our rescue as follows. I will express this as this inequality, because in fact this is the formal way of expressing the above. The above is informal, and the real meaning of this thing is that this Q minus 1 minus that A transpose A must be a positive semi-definite matrix for ellipsoid inclusion to happen. Then, once I have this, as I cannot have inverses of Q in my linear matrix inequality constraints, then I will multiply by Q to remove this inverse. But as all matrices in my constraints must be symmetrical, then I need to multiply twice by Q. Q on the left, Q on the right. Then, if I multiply like this, I will keep symmetry and the inverse will disappear. The thing is that, okay, as Q is a symmetric matrix, this transpose is not needed. Then the result of this is Q minus 1 Q, so it ends up being just Q minus Q A I whatever transposed A I non-transposed times Q. And now we have no inverses of Q, so we are closer to a linear matrix inequality. Well, it is not an LMI because this expression is quadratic in Q. So it seems that we have not solved our problem. But now what's called Schur formula will come to the rescue. First, we'll just recall that this Q matrix will be symmetric and positive semi-definite, in the sense that if it had negative eigenvalues, then the shapes will be hyperbolas, not ellipses. So we have this kind of thing, and in fact, if my ellipse is non-degenerate, then we will have strictly positive definite invertible. Good. So now, which is Schur formula in a generic case? Well, we can say that if we have some expression like this, then this is equivalent to the condition of this matrix being positive definite. Then in this case, we are indeed in this situation because, well, we just need to name this as N transposed and this as N, and invent an identity matrix in the middle of any matrix product I wish. So in this case, H is the identity. Then applying Schur formula, we get that my ellipse inclusion conditions in inverse form can be stated as posing this linear matrix inequality for each of the linear rows that generate ellipsoids I am going to consider in my black shape. So good. This is already a linear matrix inequality because we have no inverses and no squares. So Schur formula helps me transform symmetric squared matrix inequalities in some decision variables to linear matrix inequalities. Then we are happy, so we just need to encode this in MATLAB. So my new symmetric decision variable size 2 times 2 matrix will be called Q. And then I had 3 rows of matrix A defining my linear edges of my black region, and then I will encode things like this. Identity is of size 1 in this case, just to keep this matrix dimensions correct. And I will encode that for the 3 linear edges. Well, I will put here a non-strict inequality because the solver cannot solve for strict stuff. And then with the other ellipse that was non-degenerate in my edges in my black region, then I have an invertible matrix, so I will just use this thing. My Q must be smaller than the matrix defining my ellipsoid in inverse form. Then M4 was the non-degenerate ellipse in non-inverted form, so its inverse, it's the one that must be written as an LMI constraint to encode this. So with 1 of this and 3 of this, we get what we want. So we finished our linear matrix inequality constraints for my ellipse to be inside the black shape. Then we need to set the optimization problem. And of course, at first glance, making Q big could be made by making the trace big. This is a linear expression, the sum of the diagonal elements, so I can maximize it with convex optimization. And then it gives me something that, okay, it will be not that useless because the trace is also the sum of the eigenvalues. So I am maximizing the sum of the squares of the semi-axis lengths. So if you find that particular way to inflate my ellipse of interest, then you can do it. But I think that we are happier with maximizing the determinant, maximizing the area. And in fact, the determinant is the product of the eigenvalues, and what Yalmip can solve with convex optimization is the geometric mean, the square root of the product, but okay, it's just a square root if it's monotonic, so maximizing the area, maximizing the determinant can be done by maximizing the geometric mean of the eigenvalues of Q, and then Yalmip does some internal stuff to prepare it for the solvers, and this minus means maximizing, and then my convex solvers solve it in just a handful of milliseconds and obtain a Q matrix so that its area is the largest. Indeed, in particular, this is the formula of the area of an ellipse. I mean, the eigenvalues of Q are proportional to the square of the ellipse axis, then the determinant is proportional to the square area, so I carry out square root, and then this is 0.4488. It's the largest area an ellipse can have inside my black region, and if I represent them, then we get the dark red ellipse, which is the ellipse with largest area. The cyan one is the trace maximization result that maximizes the sum of the square semi-axis length, but not the area. So, it's longer, it has longer semi-axis, let's say, but the red one is the one with maximum area. And if we recall the previous video, the circumference in here is the circumference with largest radius inside the region. So we have several geometric maximization problems we can solve with convex optimization. Let us just see the areas of everything. So the red one, the maximum area one, is 0.4488. The trace stuff is just 4472. It's a large area, but not as big as the optimal one. And of course, the areas of other things we did in the first video with the ellipsoid in non-inverted representation, P instead of Q minus 1, then okay, these areas are again lower than the optimal one. then we finish with this. In this video, we have discussed how to transform my ellipse inside this black region so that my decision variable was associated to an ellipse in inverse form, q minus 1. As inverse cannot be in LMIs, we needed to multiply by q left and right some inequalities and to carry out Schur formula to get linear matrix inequalities, and then we posed as the objective to optimize the geometric mean of the eigenvalues, which is proportional to the area, and then we obtained the red maximum area ellipse. So, we have a lot of possibilities to set the optimization problem, but I guess that the two most interesting ones are the one that gave rise to the circumference of maximum radius inside here, or to the red ellipse of maximum area. So this is it. We finish with this. Thanks for watching.